Welcome. In this lecture, we're going to study about the integral test and estimates of the sum. So we are going to give the statement without proof. We're going to do some example. So suppose f is a continuous function. So suppose that f is a continuous positive and decreasing function on the interval 1 to infinity. And if the series n is the same as f of n, then the series an converges if and only if the improper integral converges too. So in other words, if integral from 1 to infinity is convergent, then is convergent too. And then B, if the integral from 1 to infinity of f of x dx is divergent, then it's also divergent. So this the function we are referring to should be a function of this. This should be the function of this one. So 2, 3, 4, 5, 6, etc. So these are decreasing function from 1 to positive infinity. So an example, test the series for convergence or divergence. So solution, the function is continuous positive and decreasing on this interval 1 to positive infinity. So we can only use integral test if all these three conditions are satisfied. The function is continuous, positive, and then decreasing on the interval 1 to infinity. So 1 to infinity of the integral 1 over x squared plus 1 dx. So the same as limit. This is how we evaluate improper integrals. So do some revision on how to work out solutions for improper integrals. So this will be given by limit as t approaches infinity of tan inverse of x from 1 to t, which will be limit as t approaches infinity of tan inverse of t minus pi over 4. So which will be given by pi over 2 minus pi over 4, which will be pi over 4. So we have a value for the improper integral. So thus one to infinity of is a convergent integral. And so by the integral test, the series is convergent. Good. So another example 2, for what values not really as an example, so let's just and just write it in the form of a theorem or a statement. The P series n power p is convergent if p is greater than 1 and divergent if p is less than or equal to 1. So as an example, the series is convergent because it is a P series with P equals to 2, which is a value greater than 1. So the exact value the exact sum was found by Leonhard Euler. Euler was born 1707 and died in 1783 to be pi squared over 6. We are not interested in the proof of the answer. The thing was to test whether the series is convergent or divergent using the P series test. Another example can say the series is divergent because it can be written as with P equals to a half, which is less than 1. It is a P series. And then there's what we call the remainder estimate for the integral test. So we say if the series AN converges by the integral test, and Rn equals to S minus Sn, then integral from n plus 1 to infinity of f of x dx is less than or equals to the remainder Rn So this is what we have. So example, approximate the sum of the series using the sum of the first 10 terms, then estimate the error involved this approximation. So B, how many terms are required to ensure that the sum is accurate to within 0.0005 accuracy. So solution. So in both part A and B, we need to know the value of this integral. So therefore, integral from n to infinity of 1 over x power 3 dx will be limit as t approaches infinity of negative a half n to t, which will be limit as t approaches infinity of minus 1 over 2t squared plus 1 over 2n squared, which is 1 over 2n squared. So part A, summation n from 1 to infinity, 1 over n power 3 approximated by S10, 1 over 1 cubed plus 1 over 1 power 2 square, 2 cubed, plus 1 over 3 cubed when you carry out this sum, you get 1.9, roughly 1.1975. So then you say, according to the remainder, estimate, we have R10 which is 1 over 2 into 10 square so therefore the size then B, accuracy within 0.005 means we have find a value of n such that Rn is less than or equals to 0.0005. Now, since Rn is less than or equals to n to infinity of 1 over x cubed dx, which is 1 over 2n square, we want 1 over 2n square to be less than 0.0005. Solving the inequality, we get n squared is greater than 1 over 0.001, which is 1000, or n is greater than square root of 1000, which is roughly 31.6. So we need 32 terms to ensure accuracy to within 0.0005. This is what we have.